Picture. Obviously, green beer means a very specific thing to brewers, but I'm not here to talk about that kind of green beer, nor am I here to talk about that abomination. But I want to talk about ways that we can make a more sustainable or environmental product. Now, Andrew made a really good point about electrification, a really salient point. I do strongly believe that that is the future of our industry. That is where we need to go to in the following years. But there are disadvantages of it, one of which is there's a massive power supply required. So really what we're going to try and look at is methods that we can do now to lower that power requirement. So I'll try and convince you why you should listen to me. And then because, one, it's the major user, the brew house itself, 40% potentially of our thermal requirements, we're going to focus in and look at that. We're going to do that through some worked examples. They're idealized, they're just to give you a feel, really. We want to look at some technologies. You will see that we did not see each other's slides before we did this. But really, I want to focus on the craft side. So I don't believe there'll be a whole lot here that's new for the big players. Hopefully they'll learn something, but I think it's much less likely. What I really want to do is touch at what's available to the guys that are producing slightly smaller volume. So I'm James Doran. I am obviously from Northern Ireland. I came over here to study, and during my studies I went to Burton Brewery. I liked it so much I came back, fell in love with the place and the product. So I was there for a number of years before I jumped ship to what was Lorien Engineering. It is now NIRAS, which is just based in Burton as well. And from there I've got to work on projects on a number of breweries, but I think I'll always still consider Burton Brewery my home, my place to be. So, as we've already said, we are looking at the brew house, and what we really want to focus on is the hierarchy of waste reduction, which seems to be the fancy new name for what we all knew as reduce, reuse, recycle. We want to try and attack it in that order. Where we can, we don't use energy, and then where it is kind of, we have used it, where can we recover it as much and reuse it somewhere else? Recycle is really about materials, truthfully, so I'm not going to talk on that today. That is more likely something that's going to come through packaging. But what I really want to focus on as well is that those smaller scale guys are suffering economies of scale on this. This is from the Beverage Institute's energy reporting figure, and we can see that at below 50,000 kilolitres, if you can see that, because we don't want to work in barrels or hectolitres, apparently we use something else. Our energy usage up at 2.61 compared to 0.73 for the next, so it's a huge jump, and that is something that we have to try and overcome essentially. The main thing that I probably want to put forward to you guys is, as you'll all know, we start cold and we end cold in the brew house. Everything in between, all the fancy heating, all the cooling, we do for a right reason, but we pay for the privilege to do both of it. So where we can, we want to see where there's overlap or synergy, we can use that. For my worked examples, I've made up a fake brew. Very happily, I can straight away say that that's about a 5% brew, because I learned that today. Don't focus too much on it. The key things that we're looking at here is we're making 50 hectolitres, we're boiling at about 6.3%, and we're going to do a stepped mash as well. So in our mash vessel, we'll raise the temperature. And this is a very simple look at what our brew house looks like at the beginning of this. So if we're going in to design a new one, or we're taking a look at what is existing, what I really want to put forward is get the things that are low cost out first. So first of all, especially in new installations, what are people of a similar size doing? and a lot of benchmarking tools exist for you to kind of compare and contrast with what's available. From there, I really want to say, what are you using? Now this takes instrumentation, so it probably is quite expensive, but it allows for development of what I'm going to refer to as your water balance. And I'll keep coming back to that, but it's essentially what water are you using, where, and at what temperature. From there, insulation, critical. Let's not throw away heat when we can. So us engineers do love talking about a surface area to volume ratio. You're losing temperature on your surface area. As you scale up, your volume increases by cubed, your surface area increases by squared. The larger you are, the less of that ratio you have to lose heat. So again, much more critical for the small guys. And it is the principle that we talked about on a heat exchanger earlier. The boring bits, but bits that always come through. Pipe sizing. So pipes are expensive. 316 is expensive, as we've learnt, and there can be a tendency to go smaller or as small as you think you need. That can have knock-on effects, however, on your usage of pumps and the energy that you draw through that because of the pressure losses that you're seeing. But equally, the opposite is true as well. So going too big, we lose some of that turbulence that we actually need to adequately CIP and clean. This is a real example of a water cooler heat exchanger that we'd see. Generally, all you really need to look at is the downward trend that we're seeing of subsequent brews. And that is simply that they were fouling each time. So making sure that you have the correct size that you can CIP that effectively and reset to 0, and get the right turbulence for heat transfer is a must. As is always drilled into me by a colleague of mine, that is your rough volumetric flow rate for equivalent pipe sizes. So you can see the impact that it can have on your CIP set if you go too large. So our first part of the brew house, as we all know, where we're inputting a lot of energy, is obviously in mashing in. There is a lot of calculations there, to be fair, that we don't need to focus on too much of. But for the brew that I presented, you can see that on that we're spending just short of £7 per brew itself. Back one more. There we go. Now I'm going to talk about something that's going to make people very upset, which is the liquor to grist ratio. So water is a really good thermal battery. It takes a lot of energy to raise it by 1 degree. There can be a saving in terms of heat by reducing the amount of liquor that you're putting in per kilogram of grist. There is a massive trade-off in that, which is your extracts can suffer horribly. What I would like to point out, but we don't talk about it too much here, is there's an emerging technology from Buehler that they're referring to as dry dehusking, in which they are essentially removing husks and removing starch from that kind of takeaway. They're inputting it back into the system, into the mash tun, the large tun, which is reporting 2.5% extract improvements, and they are starting to quote things like 10% overall brew house capacity. They're the only ones that I can come across that are actually using this technology, but it is certainly one to watch out for as a potential balance for the issues that you can see if you were to change your liquor to grist ratio. As I spoke about before, and this is really just to show that we're adding heat in another place, we're also doing a step mash, so we're trying to maximize where we are at in the brewer's window. It can be interesting to note that a mash, a sugar water, is easier to heat than water on its own. It has a smaller heat capacity. However, your method of heating is vastly different. We're attempting to put heat into a vessel as opposed to a lovely heat exchanger that's been designed for a massive surface area and that transfer. But just to note that along with my £6.70, I am effectively at £7.50 a brew. that I am having to spend, but I could recapture it. So wort preheat systems probably aren't new to anyone here. I'd say most people are using it to some degree. If you're not, it's excellent. It is the process of taking that heat prior to pitching, which is waste to us, we don't care about it, and using it to preheat your incoming brewing liquor straight away. What might be new is the methods that you use to optimize that. This, again, took some getting used to in my head, but is a real world example where a brewer was trying to eliminate the seasonality effect. So when they were having hotter brewing liquor in summer, they were actively cooling that on the first stage of their wort cooler, which was then giving them a consistent, both cold wort for pitching and a consistent brewing liquor temperature, which they could use the way they wanted to use it. That again is where your water balance comes into effect. What temperature do you actually need to use? Also employed in this is often a third stage, where you take your hot water and you use that as the first step, running counter currently against your wort, so when your wort's at its hottest, to produce what we might call very hot water. Another trade-off in this is obviously that in doing so, you're increasing the number of vessels. So there are capital cost implications and OpEx cost savings. But heat exchangers can be adapted fairly easily. So knowing your water balance and knowing what is right for you can make large savings in the long run. So we've looked at our original and we've just adapted it so that now we have heat saving and some money back in our back pocket. And this is just the change to our theoretical brew house. My apologies for going slightly too quickly. But now, our biggest impact, generally speaking, you stop double clicking, is within the boil. So we're going to focus on that now. The graph that you can see in the next stage, again, it's a very simple one, but I just want to focus on the latent heat of vaporization. So up in the top corner, you can see that that is the energy required to take water that is already at 100 degrees, but from its liquid phase to its vapor phase. If you compare that to raising water by 1 degree is 4.1 kilojoules per kilogram. This is a huge impact to us and a huge input of energy. So why send it up the chimney and up the column? That's where you'll start to see some comparisons to talks that you've already had. We have options to capture that, ultimately. Generally speaking, we can look to use that elsewhere. We have other heat demands outside of the brew house that we can use it on. And an obvious one is in your packaging hall and filling and washing. Beside there is the steam required for our example brew, boiling for 60 minutes. So again, it's a further 8.80. We could also look to put that directly into our system. So we heard about a wort or a wash preheat. It's a very similar system, but we are using that vapor to preheat water, which we're storing at set temperatures, and we're using that to raise our wort up to a point closer to boiling, making use of the high surface area that you'll get out of a heat exchanger rather than trying to heat a tank. And those are figures that we can use, those are figures based on our theoretical brew. Anyone heard of MDR? Don't know if it's come across. It is a technology that, as we said, is employed in brew houses. Hanford described it much better than I will, but effectively you are recompressing the vapor that you've seen. Higher pressure, potentially higher temperature as well because of how those molecules interact with each other. And we can use that to, in an external boiler, an internal calandria as our main heat source. You may also come across, if you've done any research into this, TVR, which Andrew again has spoken about. That is very similar, but it's using steam at a higher pressure as almost your condensing medium. That can be very, very useful, especially in distilling, where you're putting it directly into your pot still. In an application like this, it comes with a question of, I now have a volatile, rich condensate that I don't necessarily want to go back to my boiler house. What do I do with that, and how can I treat that? So, is MVR the answer to everyone's problems? Potentially not. And that's just around the limitations of size that we already spoke about. So from an amount, just Google figures more than anything, these can be around 250,000. We don't want a payback period greater than 10 years. So realistically, you're looking for the larger end of a craft scale, where you're doing larger brew lengths, and probably most importantly, where you're brewing multiple times per day. Or you're in an area where your energy costs are extremely high. That's another time that it could be of effect to you. So when we use our values, again, we're assuming pretty much an 100% efficiency here. We are potentially saving close to £2,000 a year. That's a payback period of around 140 years. So potentially not viable. Very much not viable, sorry, not potentially at all. So if we can't capture the heat from the boil, what can we do? Well, we could try and reduce the heat that we're putting in. These are the textbook answers that I was always given as to why we boil. There's a lot of brewing and knowledge in the room that can change or alter those, but sterilization and enzyme deactivation will happen at temperatures close to boiling, does not require it. Isomerization of alpha acids will happen at temperatures close to boiling, does not require it. Volatile removal won't happen at temperatures close to boiling, but there's something that we can do to try and get rid of those. Flocculation of the hop break won't happen to the same degree in boil, but you can promote it in certain ways. Wort concentration, we can't touch. There's nothing we can do about that ultimately, but we could change our recipes so that we are matching at the temperature that we actually want to ferment. And finally, color generation, really only a matter for very, very light lagers and ales, where you are getting less of that Maillard reaction, you're not getting as much color generation. But Eddie InBev developed close to home as well in the University of Nottingham, have a patent called Simmer and Strip. Is anyone familiar with it? So effectively what they have done is bubble an inert gas through the kettle itself, and that's the kind of most important part of it. Usually CO2, usually nitrogen. Those are two gases that can be very expensive, but could be another user for a CO2 plant that you have installed, carbon capture system. And I think the big thing, the reason that I felt I had to include this, is that they will give away that patent for free for a brewery of a certain size, which they list as 1 million hectolitres a year. So that's a fairly substantially sized brewery that below that they're able to give away. So if you reduce the boil and the amount that you are boiling, obviously my previous wort heating example decreases. Doesn't mean it's not worth doing, however. So we were at 6.3 and heating to 93.8. If we go all the way to the extreme, we are coming down to only 69 potentially. That is still heat that's available, and it is still heat that you could use, and it is still a more efficient way of heating than trying to heat up the kettle itself. Let's say you're on 1,000,001 hectolitres a year, and you don't want to pay for the rights to use that technology, which is an option, as I understand it. This is very similar to an existing technology, which is just wort stripping, effectively. This is NIRAS option of that, which involves a separate vessel. It's essentially a packed column, very similar as you might see in distillation, they're not beverage distillation. That's just full of a medium that promotes high surface area. And that is then injecting steam in at the bottom against a counter current flow of wort, which is stripping out those volatiles and DMF effectively. It does require a separate vessel, as opposed to a modification to an existing kettle. And as we said with TVR, I now have a stream that has high amounts of volatiles on it. What do I do before I release that? Just the variation of our theoretical brew house with that. So these diagrams are taken solely from commercial sales figures, but they're ideas of what you could achieve based on a current state, so 100% brew house usage, getting quick wins, optimizing, lagging, making sure it's there, could be expected potentially 5%. That's your Pareto, that's your, I want to hit those before I do anything else. 80% of my effort, 20% of my effort, 80% of my outcome. Work cooling optimization, so assuming you already have it in place and you're just trimming it to make it work for you, potentially another 6%. Vapor heat recovery can range, I believe, from 40 to 50 within the brew house. This is not within the boil. Figures are much higher when you just look at the production of boil. If we compare that then to simmer and strip, you do see less in terms of what they are quoting. So there's essentially two options or opportunities, but there's one that's much more readily available to breweries of a certain size. But as everyone then does, at some point you want to change your process. Let's say you want to put a stand in your whirlpool. You want to add your hops at a lower temperature because hops are expensive and you want to get as much extract out of them. Suddenly your finely balanced water balance is completely out of disarray. That's not to say that process changes can't and shouldn't happen. It just means that any change within your brew house needs to be considered for its impact, needs to be looked at. Wort coolers can have more plates added, they can be adapted and upgraded. So hopefully, if I'm passing on anything to you, it's you can't know where you're going until you know where you are. If there is low-hanging fruit, especially in your brewery, it's obvious to pluck it. Get your water balance in mind, know where your users are. If you don't have wort cooling, it's great technology, get it chucked in, and if you do, make sure it's optimized for what you actually want. Look at boil, there are options there for what you can do, and yeah, the critical bit is don't pay for the privilege of heating and cooling in your brew house. Thank you very much. Just a quick run through. Any questions?